Introductory circuit analysis using an unconventional, intuitive, approach. Session 3.
Greetings viewers. Here we emphasize how things really work intuitively rather than blindly use mathematical methods.
In sessions 1 and 2 we demonstrated how a RC circuit can be analyzed without sophisticated mathematical tools. We discussed various stimuli like step, pulse, ramp, triangular, sine, chirp. Concept of linear circuits and its unique properties. How the circuit behavior in time and frequency domain are related, but are also different. How the same RC circuit behaves as a differentiator or an integrator. You are encouraged to review the material. In session 3 we will introduce our first nonlinear circuit. We would like to emphasize that mathematical techniques such as Laplace transform cannot be used to analyze such circuits. The first nonlinear circuit element we consider is an ideal diode. It is a two-terminal device like resistor, capacitor, or inductor. However, the behavior is strongly dependent on the direction of applied voltage. An ideal diode is perfectly conducting, that is, short circuit, for one direction of applied voltage, and open circuit for the other. Voltage current characteristics of an ideal diode is shown. For positive applied voltage, that is anode voltage greater than the cathode voltage, current tends to reach infinity. For negative applied voltage, that is anode voltage less than the cathode voltage, current is zero. A more realistic diode can be represented by the equation as shown. It expresses diode current as a function of voltage. This is still an approximate model and there are more accurate models available for different types of diodes. We now plot diode current as a function of voltage based on the previous equation. We assume reverse saturation current value to be 1 microampere, and Vt equals 0.026 volts. We observe the following characteristics. Appreciable conduction exists for forward bias and negligible in reverse. There is a cut in voltage below which forward current is small. Beyond the cut in voltage, just a little change in Vd produces a large change in current. For reverse bias, the current is close to reverse saturation current I0. We would like to point out at this point that the voltage-current relationship in a diode is not at all linear. This is in contrast to circuit elements like resistor where current and voltage are proportional to each other, capacitor where current is proportional to derivative of voltage, inductor where voltage is proportional to derivative of current. Since the diode essentially conducts in one direction only, it exhibits the interesting property of rectification. If the voltage across the diode is an AC signal with no DC component, the current will still have a significant DC component. This property is used to convert AC signal to DC. The plot below illustrates the phenomenon. The applied voltage, a sinusoid with no DC component, is plotted in blue. The current, plotted in red, shows the negative cycles to be truncated. As a result, the current has significant DC component to it. Now we make our model even more realistic by adding a resistor in series with the diode junction. This is done for the following reasons. 1. Simulate bulk resistance found in practical diodes. 2. Absorb any other resistance in series with the diode, such as source internal resistance. 3. Prevent current from reaching unmanageably high values during calculations. We treat the diode in series with resistor as a composite circuit element. Our goal is to create a voltage-current relationship for this circuit element. Using KVL, we get equation 1. Equation 2 is the diode equation introduced earlier. Our goal is to express current as a function of voltage using equations 1 and 2. Rather than try to determine current as a function of voltage analytically, we will create a table of values using spreadsheet as shown next. Then we will create a polynomial model that can be used to represent the device. Enter reverse saturation current, taken as 1 microamps. Enter Vt, which is 0.026 volts. Enter series resistor value taken as 3 ohms. Column B contains diode voltage, taken as the independent variable. Current in milliamps is calculated using the diode equation. Voltage across R. Voltage across the composite element determined from KVL. Current plotted as a function of forward voltage for the composite element. For comparison, voltage current characteristics of the junction itself, plotted earlier, is also shown. It is observed that the slope of the composite is considerably less than that of the junction alone. We just created a table mapping voltage with current. For voltage less than 0, that is reverse bias, we will use current to be negative of the reverse saturation current. For voltage greater than or equal to 0, that is forward bias, we will use a polynomial representation given by equation 3. The polynomial coefficients, which depend on reverse saturation current, Vt and series resistance, are shown. If you change any of these, and also the range of voltage applied, you need to recalculate the polynomial coefficients. There are multiple ways to determine them, and we will demonstrate a straightforward method next. We will use the voltage versus current data calculated earlier. Column B contain voltage data. Column D contain current data. Column E contains current calculated from the polynomial representation. Column F contains the square of the error between the original current data, that is column D, and one calculated from the polynomial, that is column E. The cell F217 contains the sum of the error squares. Our goal is to minimize the value of sum of error squares, that is F217. To create the polynomial coefficients, we use solver from data ribbon. Sum of mean square error is set as the target cell. Goal is to minimize sum of square error. Polynomial coefficients are varied to minimize sum of square errors. Binding conditions ensure current never goes negative for positive voltages, that is forward bias condition. Next, hit solve to get the polynomial coefficients. Now we will discuss the main focus of the present session, namely the envelope detector. We discussed a variant of the RC circuit in part 2 of session 2. We now notice that the topology of the envelope detector is similar to that circuit. The series resistor R1 is replaced by a diode. KCL and KVL equations are shown. Next we will use these equations to populate the spreadsheet. Let us start our spreadsheet. We earlier calculated polynomial coefficients to represent diode behavior under forward bias condition. These coefficients depend on reverse saturation current, Vt, and series resistance R, and also the range of excitation voltage. Our next task is to determine delta t. Earlier RC circuits allowed us to get an idea of time constant relatively easily, and we selected delta t to be at least an order of magnitude smaller than the time constant. For the present circuit, we have to estimate two separate time constants for the two directions of current flow through the diode. Then we will select the smaller of the two, and make delta t at least an order of magnitude smaller. Equivalent circuit, for the diode in forward bias condition, is shown. We approximate diode resistance in forward direction as R, neglecting the dynamic junction resistance. This makes estimated time constant lower than actual and therefore more conservative. Since R2 is usually much larger than R, the parallel combination of R and R2 is approximately equal to R. The forward time constant is therefore greater than product of R and C. Equivalent circuit, for the diode in the reverse bias condition, is shown. Neglecting the effect of reverse saturation current, the time constant is just the product of R2 and C. It is usually safe to neglect the effect of reverse saturation current since current through R2 or C is much higher than that. As R2 is usually much greater than R, the reverse time constant is much greater than the forward one. Therefore, for determining delta t, we will use the forward time constant, namely, the product of R and C. We need delta t to be much less than product of R and C. Back to the spreadsheet. Capacitor C taken as 100 pF. Resistor R2 taken as 1 kΩ. Forward time constant found to be 0.3 nanoseconds. Delta t selected as 1/10 of forward time constant, that is 0.03 nanoseconds. Incidentally, reverse time constant estimated to be much higher at 0.1 microseconds. Next we define the excitation. We take the excitation as a sinusoid of amplitude 1 volt and frequency 100 MHz. We can set the phase to our choice. The operating frequency places the circuit in the realm of radio frequency or RF engineering. Time is in column A. Excitation is in column B. Before starting the KCL and KVL equations, let us take a look at the initial conditions, that is before switch is closed. The only element capable of storing energy is the capacitor, and it is assumed to contain no charge. Therefore all the initial conditions are 0. Now let us write down the KCL and KVL equations as we did earlier in sessions 1 and 2. The voltage across the capacitor cannot change instantaneously after the switch is closed, and therefore stays same as initial condition. Voltage across the diode is determined from KVL. Now we calculate the current through the diode using the polynomial representation described earlier. Please note that we calculate current without considering the sign of the voltage across the diode. As the polynomial representation is valid only for forward bias condition, we will make a correction for reverse bias condition next. Now we make a correction for reverse bias condition. We take the reverse saturation current as the current through the diode under reverse bias condition. For forward condition, of course it is the polynomial representation as before. Column H therefore contains the corrected current. Current through the load resistor R2 is obtained from KVL. Current through the capacitor is obtained from KCL. Derivative of current through the capacitor is now calculated. Current through the capacitor after time delta t is now calculated. Now we calculate the voltage across the capacitor after time delta t. All other variables use the same formula as t equals 0 plus. Now we will discuss results from our calculations. 2 cycles of the stimulus sinusoid is shown. Let us consider the first positive half cycle of the stimulus. The diode is forward biased most of the half cycle and therefore the capacitor gets charged. Significant forward current flows through the diode. Let us take a closer look into the working of the circuit. In addition to the 3 parameters shown earlier, we have added the voltage across the diode in the plot. We notice the diode is forward biased only during the periods of time shown. When the diode is forward biased, substantial current is flowing to charge the capacitor. Due to the flow of forward current through the diode, the capacitor keeps receiving charge and as a result its voltage increases. When the diode is reverse biased during the periods shown, the capacitor cannot receive any charge from the source. As a result, it discharges through the load resistor R2 and voltage across it decreases. The reverse saturation current of only 1 microamps is flowing to discharge the capacitor too. However, its contribution is usually negligible. Let us now look into a larger number of cycles. We observe that the capacitor voltage is nominally DC with a small ripple. It reaches close to steady state in about quarter cycle of the excitation sinusoid, that is 2.5 nanoseconds. Peak value of current spikes through the diode reach close to steady state peak value after couple of excitation cycles, staying just enough to replenish charge loss due to discharge through load R2. You are encouraged to change the following parameters and observe the effects. Capacitor C. Load resistor R2. Frequency of excitation. Phase of excitation. You are also encouraged to try out non-sinusoidal excitation signals. In wireless communication, we modulate a sinusoidal radio frequency carrier signal, say at 400 MHz by an information signal, say a train of random pulses. Then we let the modulated carrier radiate in air. The radiated carrier is picked up at the other end, that is the receiver, which tries to demodulate the carrier, that is, recover the information from the carrier. A very simple modulation technique is on-off keying, where the RF carrier is switched on, or off, according to the information pulse being present or not. Duration for which the carrier is on, or off, corresponds to 1 bit of information. Let us find out how successful our envelope detector would be to demodulate pulses of 30 nanosecond duration modulated on a 400 MHz carrier. Maximum voltage across capacitor when carrier is on, is 0.58 volts. Minimum voltage across capacitor when carrier is off, is 0.31 volts. The difference between these two levels is 0.27 volts. We would like to have this difference as large as possible. You are encouraged to find the optimum combination of C and R2 that maximizes the above number. However, please be aware that you cannot make C too small as then the ripple becomes excessive. Same applies to R2 as well. Making it too small may make the output voltage unacceptably low. In a practical situation, there may be more than one off or on bits successively. This needs to be taken into considering when designing a practical system. This concludes the discussion on a diode envelope detector circuit, the first nonlinear circuit in our series. This type of circuit cannot be analyzed by traditional methods such as Laplace transform. As you see, we have analyzed the circuit quantitatively using our simple technique. We have determined the transient behavior of the circuit, which is essential in using it as a demodulator. Hope you liked the video. Thanks for a patient hearing. We plan to come up with more exciting videos. Please feel free to comment or email if you have questions, comments, or need benchmark spreadsheet files. Till then, stay safe, and stay tuned.